All right, so hopefully I'm audible for those that are online. You can quickly. Looks like I am. All right, so welcome. Thanks for coming today and being brave to learn about a topic that is or can be somewhat obscure. And I guess that there's a lot of activity going on, but it's not really mainstream yet per se. So a little bit about me, but I won't spend too much time on that. I'm a product manager at a cybersecurity company. I focus on data security, primarily looking at things like data exfiltration, insider risk, and things of that nature. I am a data nerd at heart, was one of the organizers for the Southwest Florida Data Group, and I'm currently pursuing a graduate degree in cybersecurity at Georgia Tech, where I'm focusing on a little bit of what we're going to talk about here today. So first, a giant disclaimer. I'm not a quantum computer expert, and I don't claim to be a quantum computer expert. Some of the things that are being said here may not be 100% accurate, and the best I can do is just present this information so that you can get interested enough in this topic so that you can, if you would like to kind of like dig deeper and start learning more about it. But this is meant to be an introductory overview. We're gonna not go into a ton of detail on certain aspects. So let's start talking like, what are quantum computers? Maybe you haven't heard about this before. So it's a next generation of computing, basically, and it's based on the principles of quantum physics and quantum particles, to be more specific. The reason why this is important and interesting is because there's a lot of potential for this technology. There's a lot of applications. I'm going to talk a lot about what use cases are interesting for quantum computing. And this is not necessarily a replacement for classical computers. Like, there's a misconception out there that when quantum computers arrive, there's going to be no more other type of computing. These are optimized for very specific types of problems. So they're going to be very efficient at solving those problems, but that doesn't necessarily mean that we're going to not have any other type of computing. So I said quantum mechanics, quantum particles, some very abstract topics. This is a very short video. I wanted to give you like a quick intro so you get an idea. I'm not sure if the sound is going to come through here in the room. So if it's not loud enough, I can summarize it, but it's like 30 seconds or 40 seconds.
Brian Cox, without hesitation, repetition, or deviation, can you please explain for us as succinctly as possible? I have a timer here. The rules of quantum mechanics. Your time starts now.
Well, the most basic version I know of is Feynman's version, which essentially says particles are particles, and they hop from place to place with a particular probability. And the probability that a particle that's at some place will be at some different place later is given by a very simple rule. It uses a quantity called the action, which is to do with the mass of the particle and the time and the distance. So you basically calculate these little quantities, which are to do with something called the action, and you add them up. So if I start with an electron in one corner of the room, and I say, what's the probability at some time later it'll be somewhere else? Then at every point in the room, you can assign a probability that it will be there at a later point with one simple rule, and that's it. Now, this is called the path integral formulation of quantum mechanics. That underlies everything else. You can get the rest from there. So it's a simple rule. It says, what's the probability a particle will move from A to B? That's it.
I'll stop the timer then.
So it's very simple, right? Or not. So, I mean, I think he did a great job at introducing the very foundational concept of how quantum computers work. But I guess to summarize it, there's very unique characteristics of quantum particles that they exhibit. And because of those, it is possible to do things that are not possible with classical computing. And we're going to learn a little bit more about that. But if you listen to this video, like the first time that I listened to it, your reaction is probably something along the lines of this face. And is, well, we're like 3 minutes into the presentation, I'm already lost at like, it's some very abstract concepts. So we can follow two paths. One path is to go into like the depths of mathematics and physics, which we're probably not going to have the time to do today. And I personally don't have the level of knowledge to do that in the first place, or we can start talking about examples and try to introduce some of the concepts about quantum physics and quantum computing through examples. So maybe let's start there. So there's this concept from the Reddit community, explain it like I'm 5 years old. I've taken the liberty to try to put like some sort of example, not just to explain specifically how it works, but this so you get a level of scale of the differences between classical computing and quantum computing. So if we consider that computing is solving a problem of some sort, and we equate that with moving a distance, moving from point A to point B, we can say that the very initial classical computers were like walking around, right? So you're moving at a relatively slow speed, you can cover relatively slow distances. So the types of problem that you can probably address are going to be limited. If we think about the more modern computers, maybe we start to think about moving distances like cars do. So you can travel a lot longer, a lot faster. You can start seeing new places, sort of thing. You can start solving new problems. If you think about quantum computers like going from the car to the airplane, or going from the airplane to a rocket ship, means you're going at extremely higher speeds than you were going with the traditional computing. You're also going to new worlds, new places that we couldn't explore because we just didn't have the capabilities or the resources to ask some specific types of questions. So given all that, let's come back to the topic and try to learn a little bit more about some of the nuances of quantum computing. So one of the first things you'll find out is that there's a difference between classical computers is because, we don't have the traditional bits, right? So if in a traditional computer, or the way digital information is transmitted today, we're usually here, we're talking about ones and zeros, or we're coding that information into this digital format where everything is represented as this binary code. In quantum computing, the main difference is that you don't have bits, you have qubits. And qubits are unique because of those physics properties that we talked about, like entanglement, which we're going to cover now. And what that means is that you don't have to limit yourself to being a 1 or a 0. A qubit can be both at the same time. What that means is you can now increase the throughput of the computations that can be achievable. And the larger the quantum computer, the larger the processing power that you're going to have. But even that's still a little bit abstract. So let's talk about two of the fundamental foundations of quantum computing, one of them being superposition. So superposition can be described as a fundamental principle of quantum mechanics that allows a quantum system to exist in multiple states at the same time. So what exactly we mean by that? If we think about a traditional computing paradigm where we're writing an application where it's looking for data in a database, you may implement some sort of algorithm that looks sequentially, and it is trying to identify data points from that database one at a time, sort of thing. If we want to try to, I guess, wrap our heads around the superposition aspect, it would be the equivalent of looking at the entire database or big chunks of the database at the same time, which would increase the speed and the amount of data that can be processed. And again, this is not a perfect example, but hopefully you're starting to get an idea of these concepts. The other concept about quantum computing is that of entanglement. So what that allows to do is something came out in the chat. All right, never mind. What that allows us to do is for two things to be something wrong here. Okay. Qubits can be entangled for faster processing by being happening at the same time, or by having the same state at the same time. So an example in the concept of programming would be if you think about a variable and you think about a variable that depends on another variable, they're dependent on each other at the same time. For the purposes of this, what that means is that if you have two entangled qubits, you can parallelly processed information at a higher throughput, which is the essence here. Sorry for the long pause. Why is this all important? So the first thing that we're trying to get to is understand the fundamental concepts of quantum computing. And now we get to the point of what are the benefits of something like this. So we're talking about it's very fast. How fast is it? Why is this important? Which is the main question. As you can see here, just an example of a comparison from IBM Quantum on the differences for a classical algorithm and a quantum algorithm and their run times. So if you can look at first, it seems like the classical algorithm it runs faster, but as you see, if we go from larger and larger computations, as we'll learn some of the use cases, you can get from a quantum computer much better response times and answers to very hard questions. So one of those things that you maybe have heard about, or it's one of the most important problems that we would have once we have a powerful enough quantum computer, is that it could break the current way in which encryption works. While they have this great potential, they can also mean that all the private data that you have ever created, even if it's encrypted end-to-end, if we achieve a certain level of computation with quantum computer, it's going to mean that all the existing algorithms are broken. So that clearly means stop generating data, right? Or let's spend a little bit of time talking about how encryption works at a very high level. So if you think about encryption, if you haven't heard of the concept before, the idea is that you can apply some mathematical construct to, in this example, a string of text. And we have seen this historically in World War II with the Enigma machine. We may have seen it even before that, where you maybe are exchanging a letter in the text for some other letter following some specific rule. But the general idea is that for encryption to work, you have to apply some sort of mathematical formula to that string, and then you end up with a scrambled text that you see here in the middle. And if you have the right keys to both encrypt and decrypt, that means that you can see the data the way it was intended to be if you are the right audience for it. Now, why does quantum computer affect this system and how things work? So one of the things that could happen is that if the world builds, again, a large enough quantum computer, you can have enough computation power to break these encryption algorithms. The encryption, the fundamental encryption algorithms that we have today are based on large prime numbers. And the idea is that if you're able to factor a very large prime number, you would basically find the key for encryption. So if we are able to apply a very large 1,000 qubit quantum computer with very good error correction, it could basically break the algorithm. And that's probably not good, right? So one of the things that is happening, and one of the most active fields of study in the quantum space, is post-quantum cryptography. So a lot of experts and really smart people that know a lot of math are trying to figure out, can we build a new way to do cryptography so that even if quantum computers are around, the computation power needed to break that is like, it still cannot do it. So that is referred to as a quantum safe algorithm. And there's a lot of companies that are trying to develop that. And there's also a lot of work from an organization in the US and other countries too called NIST. And they're trying to identify which of the algorithms is the one that needs to be chosen as the reference one to achieve this level of security. This is a whole other topic that you could probably spend like hours talking about. If you're interested in post-quantum cryptography, there's a really good podcast from the Financial Times that talks about Q-Day, and Q-Day would be that hypothetical day when cryptography as we know it today is broken. So the general concept is that part of what I'm working on it as part of my master's program now is in developing a way for small and medium-sized businesses to be able to make that transition, even when we have a quantum safe algorithm to be applied. How do we move and re-encrypt all the data that is stored today in all the organizations, all your personal photos or your messages on iCloud that is supposed to be end-to-end encrypted. If this is not, if this is broken, someone has to go ahead and re-encrypt all the world's data and be able to make it safe again. So back to the computers, right? So we're going to talk a little bit about hardware first, and then we're going to talk a little bit about software. And the question you may be asking yourself is, am I going to have to turn it off and on again? Well, we don't know yet, but there's a lot of different variations of quantum hardware. And what you see in the screen here is at least 4 different types of quantum hardware. As you see, there's a number of logos associated with each one of these technologies or approaches. And what's happening right now is basically there's an arms race to figure out which technology can be scaled the fastest, meaning which one can generate the most qubits or the bigger processor, but also means that there's the need for that big processor to be accurate. So as we'll learn a little bit later, one of the biggest challenges today with quantum computers is that we have to be able to detect when there are errors in the computations that are happening. Now, let's talk a little bit more about the hardware. So to start with, we have superconducting qubits, and these are, as the name says, made from superconducting materials. The idea here is that these materials can't lose electrical resistance at very low temperatures, and this allows them to create quantum bits, which are the basic units of the quantum computer, as we explained. The other type of hardware that we have here is ion traps. So in this one, if you remember from high school, like chemistry or physics, I forget which one, I guess would talk about it. An ion is when an atom has lost or gained an electron. And the idea here is that by using these properties, you can, in a vacuum, using these ions, manipulate them to achieve the types of what we learned about earlier about the quantum particles. You're essentially predicting the movement of those particles, assigning a probability to that, and then that's how the computation is based. So another company that's pursuing that different approach is called IonQ, and they are publishing a lot of new research that puts them pretty high on like achieving that maximum computation. But as I said, a lot of it has to do with the error correction. There's a couple of others. One is called topological, and the idea here is that the qubits are more resistant to noise without necessarily having to have as controlled of an environment. That one is being explored further by Microsoft. And last one is called silicon photonics. And the idea here is that you can develop a technology for high performance using the optical components. Now, you may, this is a video, we're not going to play it, but if you want to learn more about quantum hardware, there's a great video from Cleo here and MKBHD that they go to the quantum computing campus of IBM in upstate New York, and they kind of walk in and let them see it. And it's really hard to get into this hardware. So if you want to see like what it looks like for a superconducting quantum computer, that's a great video for you to check out. Now, this is a coders meetup, right? We talked about physics, we talked about hardware. Why don't we talk about software a little bit? So I'll first start by saying that there are a lot of different types of quantum software. The first thing you got to think about why this is so exciting as a field, as a industry, is that we have to rebuild everything that has been built for classical computers, not for quantum computers. So if you think about operating systems, algorithms, networking, all of that has to be developed for this new paradigm. So just a couple of examples here. There's like over 16 organizations or companies that are just developing quantum algorithms. So algorithms like that one for a better encryption or a quantum safe encryption is an example. And there are a bunch of companies that are also building hardware, as you learn, and then exposing that hardware so that it can be used. All right, so that's great. Before we talk about software in a little bit more detail, just introduce a couple of details about quantum software. So the first thing we can learn about quantum computers is that there's a lot of use for simulators. Why is there a lot of use for simulators? A simulator is not a general purpose quantum computer, but they can be used to study that behavior that we spoke about, like those quantum mechanics, quantum particles elements. You can take a classical computer, you use a simulator software, and you can basically emulate the way the quantum computer will behave. Why would you want to do that? Well, quantum computer processing time is very expensive. So ideally, what you have to do first is that you go ahead and develop your code like you normally would. You first build, test, and maybe you have integration, end-to-end testing, etc. What you would do with quantum software is that you would use a simulator to kind of test your code before you deploy it to the production quantum computer. So quantum simulators need to be accurate because they need to resemble the same types of behavior that you expect from a quantum computer. And they also need to have flexibility because, as you saw, there's a bunch of different hardware types. And each one of those hardware types is going to require different simulators. So again, everything has to be built from scratch. And the simulator is your way to slowly develop the different stages of your software. The other thing that's important about quantum computers, like any other computer, is compilers. So if you think about or if you're not familiar with what a compiler does, the idea is that you have some high level or abstracted version of code, and that has to be ultimately translated to the hardware so that the hardware can run it. So in the world of quantum, what that means is that we go from a pretty high level like Python, and you have to start translating that to quantum gates and quantum circuits, because that's ultimately what the code is running on the hardware. So the first thing that a compiler does is that it basically creates a sequence of quantum gates that make up a quantum algorithm. It also optimizes your quantum circuit. So if you have a particular circuit that has some redundancies in the way that you have programmed it, this could help you optimize it, reduce the I guess in traditional code, if you have like unnecessary code, it can help you like collapse and compress your algorithm so that it runs more efficiently on the quantum hardware. The other thing about compilers is error correction. So as I mentioned earlier, one of the challenges with quantum computers is disentanglement. And this means that over time, this quantum state of these particles that we talked about in the beginning can vary. So the idea is that by having error correction in the code that you're developing, you can try to address and avoid those types of challenges. And lastly, it also maps the circuit, your quantum circuit, to the hardware, which is where your software is running, essentially. So talked about quantum gates. So here are a few examples, and they're mathematical representations, but you can think of quantum gates as the different operations that are happening on the qubits or the processing side of the quantum computer. And they are basically the building blocks of quantum circuits. They are sort of similar to logic gates in traditional computers, but they are reversible, which is unlike traditional computers. So there's a number of different type of gates that you can use to build your algorithm, and we'll get a little bit into that at a very high level. So this is an example of what a quantum circuit looks like. So if you use a combination of gates in a particular order, achieving some sort of mathematical foundation that you're trying, you would end up with a quantum circuit like this one. And you see it's using or implemented using 2 qubits. And this would be the Grover's search algorithm that I mentioned earlier. This would be one way in which you can try to search for data in a database in a highly scalable, parallelized way. Okay, so 2 other algorithms, and this one I briefly covered and I zoomed through, so I know we wasted a little bit of time with the technical difficulty. There's 2 primary quantum algorithms that you're going to hear about. The first one is Shor's algorithm, and this one is the one that has to do with the encryption that we spoke about earlier. So the idea is that if you're able to implement this in a quantum computer, you could factor any large prime number. That's something you could do that, you can break encryption. And then the other one here is Grover's, as I mentioned, and the idea is that this could give you the ability to do highly parallelized data mining and solve optimization problems. Okay, so this is a visual representation of a qubit in different states. And unfortunately, given the time limits and the constraints, this is the only code that you're going to see in today's presentation. Let me see if I can move this around. All right. So what you're looking at here is IBM's Quantum Composer. And this is, you can think of it as an IDE of sorts that lets you build your quantum circuit. That's what you're seeing on the top middle there. What you see here on the left side are the different quantum gates that are available to you to build your circuit and your algorithms. And what you see here is the output code that is basically a high-level abstraction of that. The neat thing about this environment, and as we'll learn about the other ones, is that it lets you develop your circuit or your algorithm on here, but then eventually it gives you the ability to, even for free, run it on a quantum computer. All right, so we spoke a little bit about the hardware, we spoke a little bit about the software. It wouldn't be a coders meetup without making fun of programming languages. So we're definitely going there. So let's go back to the slides here. So one of the things you gotta realize about this quantum programming in general is that, as I mentioned, there are different ecosystems that are aligned to a specific type of hardware. So I'm done making jokes about Python. Here's a more interesting slide. The interesting part here is it gives you a very good breakdown of the different hardware types. Those are the vertical or the columns here. And then in the rows, you have the different levels of the quantum stack. This is a little bit outdated. I couldn't find like a more up-to-date one. But what you need to understand here is that there's a lot of tools that are available. So if you look at the top left under IBM, it says Qiskit. That is a set of libraries and frameworks that are implemented in Python that you can use. And you can actually build this code in this abstracted library, and you can run it in different types of hardware. So you're not tied. So it's kind of the similar thing we see with traditional programming, where you have some languages that are cross-compatible, I guess, across devices or across different platforms. There's a whole lot of that has been done. So there's a few options you have. You have Q#. So there's if you're a Microsoft person, Microsoft has implemented their own programming language called Q# that is integrated with Visual Studio. It's also integrated with their Azure stack. So if you're more familiar with the Microsoft way of doing things, you also have an option for that. There's Cirq or Cirq that is what's developed by Google that also gives you basically yet another way to do the same type of programming. And as you see, there's a wide variety here, but I guess what you should take away from this slide is that there's a lot of tools, documentation, and communities that can help you get started on this. And there's a lot of things that are already there. You don't have to start from scratch. That's the main essence. All right, so you got code, you got to run it somewhere. You run it on the cloud, of course, but there is no cloud, right? So if you have affinity to Amazon, Amazon has developed a product that they called Amazon Bracket, that is an end-to-end development environment like the one we saw for IBM, but the Amazon flavor of that. The language, or you basically program in Python, but this contains all the different things that you may want to need: a high-level programming language, a quantum simulator, which you need for testing your code, and then it gives you the ability to run your code, as I said, in multiple hardware interfaces, or you can run it in multiple types of quantum computers. As I mentioned, Azure also has their own version of that, and the one we saw, IBM, also has their own version of that. All right. So far we've only talked, I guess, well, we talked a little bit of bad news about the encryption side of things, but we talked a little bit mostly about how great and exciting quantum computers are, because they allow us to process significantly more data faster, all that. But there's also some challenges with quantum computers, and one of those is decoherence. If for some reason the hardware in which you're running your computation loses their state that they have to be. As we mentioned, maybe they have to be in like very low temperatures. Maybe there's electrical or radiation that affects the way that the hardware works. There can be things that interfere with the way the quantum computer works. So, and one of those challenges also that exacerbates the longer the computer is. So if you have a 2-qubit quantum computer, you can probably contain it, and that environment is a little bit more controlled. But once, as we said, we need to grow exponentially the number of qubits that are in a quantum computer to achieve that target state. That means that you start having those scaling problems with the hardware, meaning how do you keep it consistent, constant, all those things. So the presence of noise, the size of the system, and the distance between multiple systems could also affect all of this. So long story short, there's a lot of great progress being made here, but this is the biggest challenge for quantum, and this is why the timeline is a little bit further down the road. So to give you an idea, it is expected that Q day that I mentioned where encryption is broken would happen sometime between 2027 and 2035. There are fairly more optimistic people that think a scalable quantum computer is going to be achieved before those timelines, and there's people that think the opposite as well. But I would say, based on what I've read so far, like most of the experts say that within the next 10 years, maybe 15-year tops, there's going to be a scalable quantum computer that is going to be able to achieve these things. And this is largely great news, in my opinion. So one of the things that you can achieve, so we learn a little bit about how they work, like the components. Let's talk a little bit about like the use cases and why this is all interesting. So there's a lot of different types of problems that we have today that require a lot of computation. One of them is drug discovery. So if you have this type of device that can achieve these algorithms, assuming that the hardware scales, you can basically be able to do the simulation of protein folding, which is necessary to see like what kind of pharmaceuticals attach to cells in your body, and being able to develop better medications, better drugs to treat diseases. That is one of the great things that can be achieved with this technology. The other thing that can be done is DNA sequencing. So as we have learned since the Genome Project started a while back, there's a lot of great progress that has been made in identifying genetically transmitted diseases or genetic malformities or variations that can affect your health. So by understanding the human genome in a lot more detail, thanks to this computation, we could also potentially find new cures for diseases that we don't have today. And that's generally great news for everybody. And the last thing that in the biological chemical world is that the creation of catalysts. So if a catalyst is basically something that triggers or accelerates a chemical reaction, and that is good because if you're building or manufacturing high-tech type things, or even things as simple as plastic, you can find new catalysts to have those chemical reactions that can mean that we can produce and manufacture new types of goods or things more efficiently. We can use resources better. Again, generally a good thing. Another set of use cases is all about optimization problems. So the most classical problem you hear solving with quantum computers is the traveling salesman problem. So if you have a person that needs to travel to multiple places, how do you optimize their travel to minimize the distance they cover, the cost, and all those things? But that easily translates to a lot of different industries. And the same type of optimization could be used to model the way the economy works and financial markets. So there's probably going to be mixed reviews in the room about whether or not you think that hedge funds having this level of computation to understand the markets better is going to mean better investment returns for them, but not for everybody. And there's going to be a whole ethical debate about who has the resources to achieve this level of computation and who's going to continue to, make more money, whatever the case may be. But there's a lot of finance implications, even for the average person. The retirement you have in your 401k, if there's better investment decisions, that means that you'll retire with a much better salary by the time that you retire. If the retirement age doesn't go to 80, but that's a whole different problem. All right, scheduling problems. So there's a number of scheduling problems that could also be solved can also be thought as optimization. So if you have constraints with start and end times, if you think about recent developments in data center management, where Google applied machine learning in order to improve the cooling of their server racks in their data centers, that's an optimization scheduling problem. If you think about something as simple as planning the routes of school buses going around, that is an optimization problem. So again, there's a lot of great utility and potential for the technology in that. And last but not least, I see we got some machine learning fans here in the audience. Obviously, quantum computers and the way that they're built could help significantly to optimize parameters in machine learning models. So what that means is you can, if you, correct me if I'm wrong, but I think the last time I heard, like the current variation of ChatGPT requires something along, or the ChatGPT 4 requires something along the lines of like $500 million of computational costs to be able to build that model. So imagine what you could achieve potentially with a quantum computer. You could build models better, faster with this kind of hardware. All right, so as I mentioned, I'll finish in a bit of an sad note, but it's also a happy note at the same time. So as we heard, even though there's all this great potential for this technology, there's still a lot of limitations with the way quantum computers behave today. So there's the hardware limitations, which we spoke about, and that's all about the way the hardware works, how do we scale it, et cetera, et cetera. There's also connectivity, which I miss completely here. But if you think about, like, how do we even start hooking up the quantum computers to the classical computers? If you have all your data in classical systems, how do you at scale move all that data, or progressively move that data to the quantum computer? That's a problem that still needs to be addressed. Networking in general, if you now have clusters of quantum computers, how do you figure out what's the optimal way to connect all these hardware together? So again, a lot of open questions and challenges there. That just means opportunity as well. And then you have, as I mentioned earlier, all the hardware that we have for classical computers have to be rebuilt for this new type of computing paradigm. So operating systems, more libraries, better simulators, better compilers, all these things have to be developed, enhanced over time. So it's a lot of opportunity for everybody in this room, if this is of interest to you, to start thinking about how to improve the way these things work. All right, so that is the end or the beginning. If you're excited enough about this technology and how it works, this means that maybe you'll go ahead and try to learn more about it, and perhaps start building the next quantum application. That's all I have. Thank you. Any questions? Yes. Sure. I'll repeat the question for, I'm not sure if it's heard. So the question was, it was mentioned that the quantum computers wouldn't replace classical computers. Why is that? Is it an architectural limitation? Is it some other type of problem? I think this goes back to what they're good at, what they're optimal for. So if you think about machine learning, now we're in the third wave of AI where everything's going AI, et cetera. But this happened probably like 5 years ago or 10 years ago. And there's different waves. And the reason why I say that is because there are specific problems where this is where you get those yields of like that exponential better processing for optimization problems, for specific type of tasks. But if you are doing another type of task, like if you're rendering video, this is, well, the way it works today, it wouldn't help with that. So if you're doing other types of workloads that are not meant to be optimizing for process improvement or optimization, then it's not great. It's the same thing as like, why do we have a laptop chip? Well, Apple's changing that a little bit, creating their own chips, but we have like, you know, IoTs have their own type of hardware, phones have their own type of hardware, computers have their own type of hardware. They're designed for better battery life. They're designed for better, I don't know, connectivity to the internet, whatever the case may be. So the idea is that that is the case because computers, our computers today are great at certain things. These computers would be great at different things. And that's why they wouldn't replace them. But I mean, it's hard to predict the future. So yeah, so using AI to figure out quantum problems. Yeah, I'm not familiar with that. I would say again, from my limited understanding, I would say the majority of the problems that I described today are more like physics problems rather than software problems. So I think once we get to the point where we figure out like whether we can have a quantum computer that doesn't have to be in space-like temperatures, maybe that's going to change things. If we figure out a quantum computer that can scale to 10,000 qubits without losing its state, my understanding is that AI wouldn't be able to answer that type of problem. That's more like a hard physics problem, like, you know, re-engineering, rethinking about how you build these things in the first place. For software, it could be, right? So as we were seeing, there's a lot of applications using generative AI for writing code. Potentially, that could mean that if you're writing this quantum software for the first time, you could have some sort of co-pilot that helps you develop, and you don't have to start everything from scratch. Those are, I guess, some things, but yeah, I'm not sure how much faster AI is going to develop and whether or not it can go further than that. Right. Yeah, that's a good point. So yeah, so using some sort, yeah, I haven't gotten into, I don't want to speak something I'm not familiar with, but I agree with you. So it would be something like finding patterns in the output data from running the algorithm and trying to, I guess, reverse engineer what went wrong based on the logs or something like that. Yeah, I agree. That would be a pretty interesting use case.